Hey everyone, today we explore the design of a global payment system, much like PayPal, that handles high transaction volumes and serves both merchants and consumers worldwide. I'll walk through each step of the design, discuss how various components interact, and analyze the trade-offs involved in making key architectural decisions. This is especially relevant for those preparing for system design interviews at leading tech companies like Meta or Google. So let's get started. Before diving into the system design, let's quickly clarify two key components, the payment gateway and the payment processor, which I have previously explained in depth, but at a high level, think of payment gateway as the bridge between the user's device and the payment processor. It securely transmits payment data from the user's device to the processor, handling the encryption and authorization of the transaction. For example, when you enter your card details on a website, the payment gateway encrypts this data and sends it for approval. And once the payment data reaches the payment processor, it communicates with the user's bank or card network, like Visa or MasterCard, to validate the payment information. It confirms available funds and completes the transaction. It's the engine working behind the scenes to ensure the money flows from the user's bank to the merchant's account. Now, first and foremost, let's clarify the requirements to ensure we are all on the same page. Here, we are designing a global payment system accessible to users worldwide. Both merchants and consumers are our primary users, and the system supports one-time payments, recurring payments, refunds, and dispute resolutions. It can also handle multiple currencies with real-time exchange rates. The system should scale to handle transaction volumes similar to PayPal, which means thousands of transactions per second. It must also meet international and regional regulations like PCI DSS and KYC requirements. As far as non-functional requirements are concerned, it should display high reliability, scalability, low latency, and top-notch security. Understanding these requirements and discussing them with the interviewer will set the foundation of your design. Now, our system goals should align closely with the requirements. So when we talk about high availability, aim for 99.99% uptime. It should be efficiently able to handle peak loads and grow with user demand. It should implement robust measures to protect data and transactions, ensure quick and seamless transaction processing, and you must design the system to easily add new features or support additional currencies and payment methods. With these goals in mind, we can start architecting the system. Alright, we'll first break down the architecture of a high-performance payment system, focusing on three key layers: the client layer, the service layer, and the data layer. First, the client layer. This is where users interact with the system through web apps, mobile apps, or APIs. It is responsible for sending requests like login or payment initiation to the backend. Next, we have the service layer. This is the heart of the system. Here, various microservices handle business logic, like verifying account balances, processing payments, and interacting with external gateways. These services communicate asynchronously through message brokers like Kafka, ensuring scalability and fault tolerance. And finally, the data layer. This is where all the important data is stored. Relational databases handle transactional data, NoSQL systems manage session data and logs, and caches like Redis store frequently accessed information for fast responses. Together, these three layers will ensure the system is scalable, reliable, and high-performing. Let's start with the client layer. The client layer is the front-facing part of the system that interacts directly with the end users, both consumers and merchants. This layer is responsible for user interfaces and making requests to the backend services. It can include web applications or web portals where users can log in, manage accounts, and make payments, etc. It can also have mobile apps, iOS or Android, used by customers to initiate payments, check balances, and so on and so forth. And finally, the API consumers, the third-party systems or services interacting with the payment system via APIs. For example, merchants integrating payments into their own websites. Next, the service layer is the core of the system that contains all the business logic and microservices responsible for processing user requests, handling payments, managing users, and more. This layer is the brain of the architecture where various microservices interact, data is validated, and external systems are called. Now, again, a payment gateway is the service responsible for securely transmitting payment data from the customer, for example, a web or mobile app, to the payment processor or bank. It handles tasks like encryption of the payment, for example, the card details, authorization of the transaction with the issuing bank or card network, fraud detection such as doing initial checks, or routing the request to the payment processor. In our design, we will use Amazon API Gateway as the entry point for all requests. We will later combine it with payment service and possibly parts of the fraud detection service to play the role of the payment gateway. These components securely transmit the payment data and interact with external payment processor or banks. It's also responsible for rate limiting, request routing, and user authentication, making it general gateway for all API requests. A payment processor is the engine behind the scenes that processes the actual payment after receiving the data from the gateway. It communicates with card networks such as Visa or MasterCard, banks, both the issuing and the acquiring bank, and it also handles the financial transactions including authorization, capturing funds, or settling the payments, etc. In our design, the payment service, account service, and the transaction service are performing the role of the payment processor. They verify user balances, initiate the transaction, and interact with banks or external payment gateways. They also handle currency conversions, they record the transaction via the transaction service, and update the account balance via the account service. And of course, they must ensure asset compliance and manage distributed transactions across services. So at a high level, we are dealing with distributed microservices architecture. This is the core logic where services like user service, payment, account, and fraud detection service interact to handle payments at scale. User service is responsible for user authentication and profile management. Payment service manages transaction processing and external communications with payment gateways and banks. Account service tracks user balances in multiple currencies and ensure integrity during transactions. Fraud detection service performs real-time monitoring of transactions to flag potential frauds using machine learning models. And notification service sends transaction updates to users. These services interact asynchronously through message queues, for example Kafka or RabbitMQ, for reliable communication and to decouple services. We will later dive into how the services themselves interact among each other. But first, let's talk about data layer. Data layer consists of relational databases for transactional data and NoSQL for fast access of logs or session data. We use relational databases like PostgreSQL for transactional data to ensure asset compliance. For non-critical data like logs and session information, we use NoSQL databases like Cassandra or MongoDB. In a microservices architecture, it's generally recommended to use database per service to ensure loose coupling and data independence. Each service owns its own data and the schema it uses, but they can communicate through event-driven mechanisms like Kafka rather than sharing databases. So, user service database stores user data and profile information, including authentication details and KYC or Know Your Customer status. Account service database manages user account balances across different currencies. This database ensures asset compliance for critical financial data. Payment service database stores metadata about payment request, such as who initiated the request, which merchant it is for, what currency is being used, and the current status of the payment. Currency exchange rates table is another form of metadata that's used when the payment involves multiple currencies. It stores contextual information about the exchange rates used at the time of the payment request. So, before a payment is processed, the payment service records metadata about the payment initiation, such as who initiated the request, which merchant, what payment method, and currency and status. During payment processing, the metadata about the payment status, such as pending, is used to track whether the payment was successful or if it is still retrying. If currency conversion is needed, the payment service looks up the exchange rate from the currency exchange rates table and uses that rate for the conversion. And after the payment is completed, the metadata in the payment request table is updated to reflect the final status, success or failed, while the detailed transaction records are stored in the transaction service database. Transaction service database handles all transaction records, ensuring durability and traceability. Fraud detection service database keeps a historical record of flagged transactions, fraud scores, and user behaviors data, which can be later used for machine learning models. And finally, notification service database stores notification logs for tracking whether payment confirmation messages like emails, SMS, push notifications were sent successfully. Now, to handle massive datasets and high read-write operations, you should mention few things during the interview. Sharding. We partition the database horizontally based on user IDs or regions. We have read replicas to improve read performance and provide redundancy. Also talk about indexing frequently queried fields to speed up database operations. I have made videos on each of these topics in depth, so do check them out to get better clarity. Now let's jump into the data in the NoSQL database. Session data typically includes details about user logins, session tokens, timestamps, and expiration times, which can be stored in a NoSQL database. Event logs capture actions taken by users or systems events, for example, logins, payments, or password changes, and they need to be stored efficiently to support high write throughput, which also can be stored in a NoSQL database. Now, for each key interaction between services, we'll be using Kafka queues or Kafka topics, which ensure asynchronous communication and decoupling. Here's the list of Kafka topics that might be in play based on the described architecture. So for example, we'll have balance check queue, which takes requests from payment service to account service for balance verification. Balance response queue from account service response with balance verification result. Transaction recording queue for payment service notifying transaction service to persist transaction data. Account update queue for notification for account service to update the user's balance. Notification queue is for message to notification service to send a confirmation to the users. Fraud detection queue is for transaction details sent for real-time fraud analysis. Payment gateway queue for asynchronous communication with external payment gateways. And gateway response queue, which is responsible for response from external gateway back to the payment service. Now, this being a microservices architecture, we are using one of the popular database per service microservices pattern. So as far as database ownership is concerned, user service owns the user database for user profiles and authentication. Account service owns the account database for account balances and currency handling. Payment service owns its own payment metadatabase for logging payment request. Transaction service owns the transaction database for storing transaction records. Fraud detection service owns its own fraud detection database for storing fraud logs and user risk profiles. Notification service owns its own notification logs database for storing notification history. Alright, now that we have laid out all the components and basics, let's explore the service layer and how these all components interact during a typical transaction flow. So, the user initiates the login process from a web or mobile app by sending credentials to the API gateway. The API gateway sits behind a load balancer which distributes the incoming request across multiple API gateways instances for high availability. The API gateway forwards the login request to the user service. User service validates the user credentials against a cached version of the user profile in Redis to speed up authentication. And if no cache entry exists, the user service fetches the user data from the user service database. If the credentials are valid, the service generates a JWT token and stores session-related data such as user ID, session start time, etc. in Redis for fast access in future requests. The user service then sends the JWT token back to the API gateway, which returns it to the client. The JWT token will be used in subsequent requests for authorization. And if you want to know more about how JWT works, do check out my video on JWT where I have explained it in detail with examples. Alright, now let's take a common example once the user is authenticated. Initiating a payment. So in this common use case, the user initiates a payment, for example for a purchase, by sending the payment details to the API gateway. The API gateway receives the payment initiation request and verifies the JWT token to authenticate the user. Once the user is authenticated, it forwards the request to the payment service for further processing. The payment service checks the Redis cache again for the user's account balance. If the balance is cached and sufficient, the payment service logs the required amount in Redis, and if the balance is not cached or is outdated, it proceeds with the next step. The payment service publishes the message queue to the balance check Kafka queue, asking the account service to verify the user's account balance. And the message might include user ID, payment amount, currency, or a correlation ID to track the request-response interaction. The account service listens to the balance check queue and retrieves the user's account balance. It can use Redis for the cached balance, and if not cached, it retrieves the balance from PostgreSQL. If sufficient funds are available, it updates the cache and logs the funds in PostgreSQL using database transactions. The account service then publishes a response message to balance response queue with a verification result, for example, balance is sufficient or insufficient. The payment service listens for the response message from the balance response queue, and if funds are sufficient, it logs the amount and proceeds with the payment processing. For example, interacting with the external payment gateway or recording the transaction. And if funds are insufficient, the payment service returns an error to the user via the API gateway. Now, since PayPal or a similar service combines both the gateway and processor roles, the service layer in our architecture implements both. So the payment gateway functionality is about receiving payment details and securely transmitting them. And payment processor functionality is validating and settling transactions by interacting with banks. However, PayPal still relies on external financial systems like bank or card networks for actual money movement. When I say card networks, it means networks like Visa or MasterCard. And when I say banks, it's for both the merchant and the customer to actually move funds. Thus, banking and card network integrations are external from PayPal's system and are necessary to complete the financial transactions. Do check out my previous videos to understand their role better. Alright, coming back to the topic, the payment service may need to interact with external payment processor like MasterCard or Visa to authorize and settle the payment. It publishes a request to the payment gateway queue in Kafka, which is processed asynchronously to avoid latency for the user. Once the external gateway, for example Visa, processes the payment, it sends a response, for example payment approved or declined, via the gateway response queue. The payment service then consumes this response and determines the outcome of the transaction. If the external payment gateway fails to respond, the payment service implements the retries using an exponential backup strategy which I have covered in my other videos. And if repeated failures occur, a popular microservices pattern, circuit breaker pattern, prevents overloading the external service. And once the payment is confirmed, either synchronously or asynchronously, the payment service notifies the transaction service by publishing a message to Kafka. The transaction service consumes the message and persists the transaction details, for example the transaction ID, timestamp, amount status, etc. It ensures that these operations adhere to ACID properties, atomicity, consistency, isolation, and durability to maintain data integrity. The payment service sends an idempotency key along with the request to the transaction service to ensure that the retrying of the payment due to network or service failures doesn't result in duplicate charges or transaction. The transaction service checks the key before committing to the transaction to the database. And once the transaction is successfully recorded, the payment service sends a message to the account update queue in Kafka, notifying the account service to update the user's balance. The account service consumes the message, deducts the payment amount from the user balance in the PostgreSQL database, and updates the balance in Redis for future transactions. After the transaction is recorded, the payment service publishes a message to the notification queue in Kafka indicating that a notification, email or SMS should be sent to the users. The notification service consumes the message and sends the confirmation via email, SMS or push notification to the user. Again, notifications are sent asynchronously to avoid delaying the main payment flow. Also, simultaneously as the payment is being processed, the payment service sends transaction data to the fraud detection service via Kafka. The fraud detection service consumes the message and runs machine learning models to flag potentially fraudulent transactions. If the fraud risk score is above a certain threshold, the fraud detection service publishes a message to Kafka to halt the transaction or trigger additional verification, like multi-factor authentication. If the transaction is flagged, the system can either roll back the transaction using compensating transactions or require additional user input. The payment service then responds to the user via the API gateway once the transaction has been processed and recorded to the system. At this point, the client receives a confirmation along with the transaction receipt, for example, the amount, transaction ID, and timestamp. And to minimize the perceived latency for the user, certain parts of the flow, like external payment processing, notifications, and fraud detection, happens asynchronously. The user receives a response once the core transaction is processed, while these background tasks, for example sending notifications or flagging fraud, continue to execute without blocking the response. To ensure resilience and high performance, we can implement a number of microservices patterns in our architecture. And it's very important for you to talk about some of the architecture patterns during your interview. Now, I have made videos on each of these patterns where I simplified them. And if something doesn't make sense, I encourage you to develop a deep understanding of them. Here, I will briefly talk about a few important patterns in the context of this system design. Circuit breaker pattern can be used for external communication with payment gateways or banks. If the external service becomes unresponsive or returns errors, our circuit breaker trips to prevent further calls. It ensures that the system doesn't get overloaded with retries. Once the external service is back online, the circuit breaker resets. For idempotent operations such as interacting with an external payment processor, retries are triggered in case of failures, for example timeout or network error. This ensures eventual consistency in operations like transaction settlement without duplicating operations. An idempotency key ensures that retrying a transactions due to network failures or etc. won't result in a duplicate charge. The payment service accepts a unique idempotency key from the client, ensuring that repeated requests with same key don't trigger multiple transactions. And for distributed transactions across multiple services such as payment service, account service, or fraud detection service, a Saga pattern can be used to ensure eventual consistency. Each service commits its local transaction and compensating actions are triggered if a failure occurs in any part of the chain. For example, refund in case the payment fails. Now, security is also a critical aspect of any payment system. In your interview, you can talk about encryption, such as data in transit, where all data is encrypted using TLS, or data at rest, where sensitive information in databases is always encrypted. You can also talk about authentication and authorization. For example, you can implement multi-factor authentication for users or use role-based access control or RBAC to limit system access. Fraud detection we are already using for real-time monitoring and machine learning models to detect suspicious activities. These measures protect both the users and the integrity of the system, and if you want to learn in detail about each of these concepts, do check out my security playlist. As we wrap up, let's think about what it takes to handle PayPal-like volumes of traffic. The key to scaling effectively lies in optimizing every layer of your architecture. First, microservices architecture is crucial because by breaking down functionality into smaller services, each one can scale horizontally based on demand without affecting the others. Next, load balancing helps distribute incoming traffic across multiple servers, ensuring no single instance gets overwhelmed. Global load balancers make sure traffic is routed to the best performing server. Then there is caching. Implementing in-memory solutions like Redis for frequently accessed data. This drastically reduces the load on your databases, speeding up your app's performance. For tasks that aren't critical to main flow, asynchronous processing with message queues can keep things fast and responsive. Offload these jobs without slowing down the user experience. Finally, don't forget database optimization. Use read replicas to handle queries that don't need to hit the primary database, and manage large datasets effectively with partitioning and sharding. By tweaking each of these layers, you can build a system that is highly scalable with low latency and high throughput.